So our next two topics go hand in hand, which is correlation and regression. So correlation is just going to kind of be the start to see what we're doing. And then regression is going to be the next step you can take if there is a correlation between things. So we say a correlation exists between two variables when one of the values of one variable are somehow associated with the values of another. So there's some kind of connection between the two. Doesn't mean that one causes the other. Correlation and causation are very different, but however, there is a connection between the two. Specifically, what we're going to be focusing on in this class is linear correlation. So a linear correlation, hopefully the word linear gives it away, exists between two variables when there's a correlation and when you plot those data values or plot those points, they can be approximated by a straight line, okay? So we'll see some examples of this, but basically if you were to plot that data, picking whatever you want for X and Y, you would see that it has some kind of line as a shape. So what we're gonna be focusing on in this section is something called the linear coefficient. So the linear coefficient which is denoted with an R, measures the strength of the linear correlation between the paired quantitative X values and Y values in some sample. So what I want to do is I want to give you some examples of scatter plots where we've plotted X and Y values. And we're going to go ahead and we're going to give an example of what that linear coefficient can be. And we're also going to talk about some important notes for this coefficient R. So to start out, the very first thing is this value of R is going to be a number between -1 and +1, and it can equal those values. If you have a positive value for R, this means you have a positive correlation. If you have a negative value for R, there is a negative correlation. And then if your R is equal to 0, that's pretty much indicating there is no correlation between the two. So to give you some examples with these plots, if we look at this first one, they are scattered, but you can see they can be approximated by a straight line. And in this case, that would be a positive value. Here, same thing, it is now just going to be negative because it is dipping downwards. If I look at this plot, they are all over the place. There's absolutely no correlation between these two. And this last one, if you notice, if you try to trace these, what you end up with is actually not a shape that's linear, but something that's called quadratic or second degree. So comparing the two that have the best linear correlation, if I look at the second example here, those dots are a lot more compact. So this one is going to have a stronger linear correlation. Both of them, though, are going to have larger R values. So in this case, this first one may be something like 0.859. And it's positive because, again, it can be estimated by a positive line or a line with a positive slope. Here, this is more compact, so it should be closer to one of these extremes, 1 and -1. And in this particular case, because it's going downward, that would mean it's a negative correlation. So this value of R may be something like -0.971. In this example, again, these ones are all over the place, so there's no correlation between these. It doesn't mean your value of R is exactly equal to 0, but it is going to be something small. So maybe in this case, you get 0.074. And then for this fourth example, again, it's not linear, but it doesn't mean you're going to have a value of R that's 0. And here you could actually get something like 0.330. Okay. Now, as just a couple extra notes, the scale does not matter that you use. So let's say you're working with temperature and maybe you have it in degrees Fahrenheit. If you change all of those to degrees Celsius, your value of R would still be the same on that different scale. The other thing, if you interchange your X and Y, won't change your value of R. So it does not matter which one you pick to be on the X-axis versus the Y-axis. It'll still be the same R value. And then the last one is the value of R is very sensitive to outliers, especially if you have a small amount of data. So if you look at this particular one, this guy over here is all the way on its own. That has a big impact in the value of R. So it's got a lot of sensitivity, okay? Now, realistically, if you are going through and calculating a linear coefficient, you are going to use technology. So we're going to use Excel for this. And even on a test, you're not going to be expected to calculate a linear coefficient by hand. You'd either be given it to you or you would have access to a calculator that could do it. I am going to go through and I'm going to show you how you can do it by hand, but the formula is very messy. So in no way, shape, or form are you expected to remember what that's going to be. But it's still something I think you need to see at some point, but I will show you how you can do it using Excel. So we're going to start with just some notation because we're going to have a lot of summation. So the first N is still the same thing. In this case, it's the number of pairs of sample data. You don't count each X and Y separately. They count as a single unit because that gives you a point. If you see the sum of something, so in this case, the sum of X, this means you're going to sum up all X values. And then these next two look very similar, but the order or where those parentheses are does matter. So in this case, the square happens after the parentheses. And in here, the square is inside. So the sum of X squared means the sum of all X squared values. Where what you would do here is you would find the sum of X first, which is this, and then you square it. So this is the sum of all X values, then you square it. And then because we're working with X and Y, the other thing you're gonna see is that we have to multiply these two together. So this is the sum of all X times Y values. R is our linear correlation coefficient. For the sample data. And again, this is going to be an estimate because we're not going to have the true population data. So the true linear coefficient is given by this Greek letter, which is rho. So this is the linear correlation coefficient. For the population data. So like I said, the formula to find R is very messy. We're gonna do it by using a table. But what you have to do is you have to take the number of data values. You're gonna times that by the sum of the XY values. Then you subtract the sum of X values times the sum of Y values. And in the bottom, you're gonna have two square roots that you have to multiply. So again, we are definitely going to need a calculator. Your phone is not going to cut it. Inside each square root is something very similar. It just depends on the X or the Y values. So in the first one, we have n times the sum of x squared values, and then minus the sum of x values squared. What goes in the second one is the same thing, but you replace it by y. Okay. So again, we are just going to do a single example by hand where we are going to find the value of the linear correlation coefficient r. So we have x and y values and we have a ton of them. So what I'm going to do is create a big table. I need to sum up x squared values, I need to sum up y squared values, and I need to sum up xy values. So what I like to do is I like to make a giant table and find each of these things, and then afterwards I'm going to go ahead and I'm going to sum it up here. So we'll find all of the values to begin with, and then we'll go ahead and find the sums after. So what I'm going to do in this column is I'm going to square each of these data values. So I'm going to trust you can do this part in a calculator. If you take 62 and square it, you should get 3,844. Next x value is 76 squared. That should give you 5,776. Next up is 50 squared, and that will give you 2,500. Next x value is 51, so that squared gives you 2,601. 71 squared is the next value, which is 5,041. 46 squared is going to be 2,116. 51 squared, we already did, 2,601. 44 squared will give us 1,936. And finally, the last x value squared is 79 squared, which is 6,241. So this finds each of these data values and squares it. Now we're going to do the same thing with y. We're going to take each of these values and we square it. So first up is 36 squared, which is 1,296. 39 squared gives us 1,521. 50 squared is 2,500. 13 squared is 169. 33 squared is 1,089. And same thing again, 33 squared is 1,089. 17 squared is 289. 6 squared is 36. And finally, 16 squared is 256. Then finally, I need to take x times y. So for each of these pairs, I'm going to go ahead and multiply those two values together. So it is x times y. So my first pairing is 62 and 36. If we multiply those, it gives us 2,232. Next up is 76 times 39, which is 2,964. Then we've got 50 times 50, which is 2,500. Then 51 times 13, which is 663. Then 71 times 33, which is 2,343. 46 times 33, 1,518. 51 times 17 is next, which is 867. 44 times 6 is 264. And 79 times 16 is 1,264. Okay. So what I'm gonna do in this bottom row is I'm then going to take all of these data values and add them together. So what this result will be is if we sum up X, this result is if we sum up Y, this result is if we sum up X squared, this is the sum of Y squared, and this result is the sum of XY. And these are all the things I need for my linear correlation coefficient formula. So again, you can use the calculator to do this by hand. What I'm gonna do is actually show you how to do this in Excel too, so you can do it on your own through Excel, but then also Excel has a function that will calculate the linear correlation coefficient for you. So I preemptively have my table over here in Excel. You can see I have all of my values at the top, X, Y, I need X squared, Y squared, and X times Y. So just to show you here, if you want to take X squared, you have to do equals, and then you want to take this and you want to square it. So the way you do a square button is a little caret, and then you square it. And you can see here, it auto-filled in all of my values, so you get exactly the same thing we found in our table. All of these match up. And then if I go into Y squared, I need to take each of these Y values and square it. So again, you use that little caret, or you can say Y times that value of Y. And it goes ahead and preemptively fills in everything. And then finally, X times Y, I need to put equals again because it's a formula. I want to take the X value and I want to times it by the Y value. So you end up with exactly the same thing. Now in this bottom row, what I want to do is I want to go ahead and sum everything up. It auto-filled in the same formula here, but I'm going to go ahead and delete those because I want to take the sum. So the way I do that is put equals, I want the sum of, I click my first cell and then I drag this down and I'm going to sum up all of the values from the second row to the 10th row. And so if I sum up all of my X's, this is going to give me 530. If you're working with a computer, typically you can drag that over, but because I'm on my iPad, I'm going to have to go in and type everything. So I want to sum up all of these values. For this would be the sum of X squared values. So I want to sum all of them up. Then I want to sum all of these up. And finally, we're going to sum all of these values up. Okay. So filling in now on my table, the sum of my Y values is 243. Sum of my X values is 32,656. Sum of my Y squared values is 8,245. And sum of XY is 14,615. Okay. So I have everything I need now to actually find my linear correlation coefficient. So I'm going to start by just writing out what that formula is. Then we'll go ahead and we'll use Desmos to actually calculate the value. So I'm going to cheat a little. I'm going to copy this down. And I've got all of my values except for n. So if I go back up here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 pairs of data values. So our value of n is 9. So filling in everything, our value of r is going to be 9. My sum of xy is right here. I'm going to take 9 and times it by 14,615. Then we want to subtract the sum of x's, which is right here. That's 530. The sum of y's is 243. And then in the bottom, I've got 2 big square roots. My first one is going to be n, which is 9. The sum of x squared is 32,656. And then here, this is the sum of x squared. So I want to take this value and square it. So we're going to subtract 530 squared. Then I need to do the same thing again with y's. My value of n is 9. The sum of y squared is 8,245. And then we need to subtract the sum of y squared. So I subtract 243 squared. Definitely a mess to plug into your calculator. So again, we are going to use Desmos for this. So I need to start with a giant fraction. So I'm going to go ahead and in here, put my fraction button. In the top, I have 9 times 14,615. Then we subtract 530 times 243. In the bottom, I have 2 square roots. So there's my first one. There is my second one. In the first square root, we have 9 times 32,656. And then we want to subtract 530 to the second. Over here, we have 9 times 8,245. And then we want to subtract 243 to the second. So this gives us a value of r rounded to 3 decimal places of about 0.196. So doing that by hand, a lot of work. Instead, we do have a function inside of Excel that will take care of this for us. So what we do is we hit equals, and then the function is correlation, basically cut off. What you put in the first column is going to be the first set of values. So our last x value is 79. And then you put the second set of values in the second spot. And in the end, you get exactly the same thing for your r value. Just to show you, it doesn't matter what you put in the first position. So if I put these values first, followed by these values, you still end up with the same r value. So it makes 0 difference which one you call x and y, okay? So again, that's the last time you're actually gonna do this by hand. You're gonna use technology to help you. But what we wanna kind of go through is how do we interpret a value of r? So it's going to depend on the amount of data values you have, and it's also going to depend on the significance level you want. So we typically use our alpha being 5% or our alpha being 1%. And what that's going to do is it's going to give us a table of values. And again, you just kind of go to the closest one. If you don't have exactly that value of n, you're going to underestimate it. So here's our table of values. Again, depending on your n, will tell you which row. And we have an alpha level significance of 0.5 or 0.1. What this table gives you are critical values for that linear correlation coefficient. And it basically is creating a rejection region for you. So depending on where your R value falls, once you go through and calculate it and find these critical values, that will tell you if there's evidence or not of linear correlation. So depending on the sample size, and the significance level, we can find critical values to tell us if there is evidence or no evidence of linear correlation. So you're gonna see, we're basically doing a hypothesis test, and you can see it down here, of that actual linear correlation coefficient being 0 or not. So one or the other is going to happen. So you're testing, is there no correlation or is there not? So we have a scale of values for what the true value of R can be. It falls somewhere between -1 and 1. And 0 is smack dab in the middle. If you're testing there being no correlation or not, you're going to get two critical values, and you use symmetry to your advantage. So if you have your n equals 4, your alpha level is going to be 0.05. You need a value of R to be 0.95 as your critical value. So it creates a value over here and a value over here. This is the positive R critical value, and this is the negative version of that. You need to be bigger than either of these values to be able to have some kind of correlation. So essentially, if your actual value of R falls in this particular region, there will be correlation. And same thing here, if your value of R falls in this side instead, that means you just have positive correlation. But if it's in between, then unfortunately there is going to be no evidence of correlation. Okay. So let's try a few examples of this. In the first one, R is already calculated for us. And then in the second one, we're going to use Excel to our advantage to figure out if there is or not. So we're told 60 pairs of values result in a linear correlation coefficient of R being 0.198. Using a 0.05 significance level, we're going to complete the following. So the first is we're going to determine that null and alternative hypothesis. So you're going to have the same one in our case every single time. Either the true correlation coefficient is 0 or it is not. Okay. So the null hypothesis is going to be the correlation coefficient is 0, so there is no correlation. Okay. Now we're going to determine the critical values. So in this case, our value of n is 60. Our significance level is 0.05. And because it is this hypothesis where you have a two-tailed test essentially, there are going to be two critical values. And they are just going to be the positive and negative version of the same number. So to figure this out, I go back to my table. My alpha is 0.05, and I do actually have a value for 60. So my critical values are 0.254, positive and negative. Okay. So we have a value of R calculated. We have the critical values. We want to figure out, is there sufficient evidence to support the claim that there is linear correlation between the two? So that would be in the case where we're essentially rejecting the null hypothesis. So putting my scale out here, -1 and +1 are my endpoints with 0 in the middle. My two critical values are 0.254 and -0.254. And then if I look back at my R value, it's positive 0.198. So that value falls right here. What I would need is for there to be correlation, I need to be on those extreme ends. So here, since this does not fall outside the critical values, there is not sufficient evidence to support the claim. So it is likely there is no linear correlation between these two. Okay. For the next one, we're going to have to actually construct a scatter plot, we're going to have to find the linear correlation coefficient, and then we're going to use that to determine if there's sufficient evidence to support the claim of a linear correlation between the two. So in this one, we are solely going to use Excel, and we are going to use Excel even to create a scatter plot. So I've got Excel up and I've got my data all entered in here. The first thing I'm going to do is I'm going to construct a scatter plot. So I'm going to go ahead and select all my data, and then I'm going to go to Insert, and then I'm going to need to go to my charts. And so I want a scatter, and then you can pick the one you want. For us, we specifically just want those values. So if I look at my data, it's going to give me this scatter plot. Sorry, those ones there. It's putting the bubbles from the green inside my scatter plot. So you can look here and we get kind of a curved, so it doesn't really look like there's a linear correlation between the two, but there is some kind of correlation, okay? So that would be our scatter plot. So I'll go ahead and I'll add this into my image, but here is my scatter plot. Now I no longer need that. What I want to do is I want to see what is my linear correlation coefficient. So again, I have a function for that. So I do equals core, and then my first set of values is here. My second set of values is here. And then I get a correlation coefficient of about 0.816. So now I want to see, is this sufficient or not to tell me there is a correlation? So I need my value of n, and if I count that, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 data values. And they tell us to use a significance level of 0.05. So if I go to my table, I need to figure out what my critical values are. So we have a value of n being 11, alpha is 0.05. So my significant level is 0.602. So I have one critical value here, which is 0.602. Another critical value here, which is negative 0.602. And if I look at where my value of R falls, that's 0.816. That is right here. So using this tells us there is sufficient evidence to support the claim of a linear correlation because it falls into that significant region. So there is sufficient evidence to support the claim of a linear correlation between the two variables. Because essentially this region is where we reject that null hypothesis, which is that the linear correlation is equal to 0. In this region is where we don't have enough evidence to support that. Now, what this tells me is there is sufficient evidence to support the claim of a linear correlation, but because we have this scatter plot, we actually know a little bit better. If I just went and calculated R, found the critical values, fantastic, I think there is linear correlation. But this scatter plot reveals there's actually a different kind of correlation going on. So the scatter plot reveals a distinct pattern. That is not a straight line. So although it's important to find these values of R and do this hypothesis testing, we would miss a lot of information without that scatter plot. So you always want to utilize that to your advantage.